I don't actually know whether, do you believe twistors are a more fundamental description of the world?
Well, I do, yes. I mean,
Okay.
I don't normally say that out loud, but now you put me in a position, yes. No, I do
think that's
so, yes.
fucking great. I mean, in other words, it's like you have to say this I believe, and in general, people won't say it.
No, I think the thing is that I have been driven in directions, just as you're pointing out, in directions which are picking out the particular rather than the general.
Right.
So, sure, you have mathematics, which one of the huge aims in mathematics is to be more and more general. And you mentioned the Atiyah-Singer theorem. That's a beautiful example of that, where it simply generalizes over areas which you would never thought.
But it also particularizes. So, for example,
yes,
it is only in low dimensions where you get to play the game with what are called deformation complexes, where the first term is the symmetries in the problem, the second term is the fields or the waves in the problem, and the third term is the equations in the problem. And then you get to cut it off at that point and have that be this magical concept of an elliptic complex. So, for example, in dimension 4, we gleaned something bizarre, which is that there are an infinite number of different ways to do calculus in four-dimensional space and only one way to do it in every other dimension.
Yes, yes. Well, there's something special there about 4. Certainly, that's true. And the connections, maybe not that clear at the moment, but maybe we will see that this is...
Maybe differentiable structures are part of physics.
It's quite possible, yeah.
How amazing that... I'll give you another very bizarre one. I don't know whether this has ever come up. If you have two sets of symmetries known as Lie groups that act transitively on the same sphere in usual position, then either their intersection acts transitively on that sphere or the dimension of that sphere is 15. And I believe that the intersection of the groups looks like the electrostrong group. So it's very close to the particle spectrum of theoretical physics, pulled out of nowhere just from talking about sphere transitive group actions.
Yeah. Well, it's clear that in particle physics, I've never really been somebody who studied particle physics closely.
Is that right? I didn't know.
Well, in general way I have, but I suppose I thought we're maybe a long way from really understanding what's going on there. I don't know. I hope that...
I didn't know that.
Well, we have... No, it's a complete... I often have heard different views from people on these things.
I think we're almost at the end.
Well, that's an interesting suggestion.
So how do you come to the idea that we may be quite far?
I'm not saying that we're necessarily far. I think it's understanding why the groups are the groups that we see. And people have different theories about these.
Well, let me ask you then a couple of questions.
Go on.
So very early in this new stagnation post the Standard Model, people like Glashow and Georgi and Petit and Salam put forward these unifying symmetries that remain very odd because they're so attractive and powerful. The prettiest of them being something called spin 10, which physicists persist in calling SO10 for reasons that escape me.
Yeah. Well, this is the one which doesn't exist, or is that not that one?
Well, the original SU5, which sits inside of spin 10, was disproven in its most basic form. And at that point, Georgi and Glashow had been trained in the previous culture of physics, which is that you fell on your sword when you predicted something and it wasn't true. And I think that they sort of rushed to commit ritual suicide far too quickly.
Yeah. Maybe if I'd worked in the subject, I'd form a clearer view. It's just that from the outside, I'm not convinced that... Clearly there are things which people have discovered which are absolutely fundamental in particle physics. But somehow it hasn't got to the basic level which I feel I can see why these groups are what they are and so on. Let me not talk about it because I'm not an expert at that and I'm only giving an impression. And I suspect there will be, maybe not too long from now, a better understanding. I'm hoping that twistor theory might have something to say about it. But at the moment, the area which needs to be explored here hasn't been explored. The things we did at one time, I'm sort of deviating a bit from the general trend. But there was a question of how we treat massive particles in twistor theory. And naturally, twistor theory describes massless things. Things go along the light cone and that sort of thing.
So in other words, because you privileged the light cones, then the treatment of particles that were massless got a privileged treatment.
They have a privileged treatment. And not just that, you find transformations. There's a way of representing the Maxwell equations. This is the thing I was mentioning about the TV program. Way of describing the Maxwell equations, which you get out of twistor theory, and it comes directly out. What about the Dirac equation? You want to talk about massive particles. Well, the way it seems to lead you is you think of you see a massive particle has a momentum vector, which is time-like, so it points within the cone. And one way you can describe a time-like one is think of two null ones or two light-like ones. So you think of a zigzag. So it's got a zig and a zag. And that's one convenient way of doing it. Or you might have one which is made of three, zigzag, zog, something like that. And you can get the time-like line out of...
So you can build it up from different primitives.
That's right. So the argument is that you have a twistor for each of these zigs and zags. And so you might have two of them, you might have three of them, and you see how many of them give you the same, and then you get these groups in twistor theory. And these groups look like the particle physics groups. So you've got SU2 and SU3. And the idea we had is, that's the basis for these particle physics
So SU2 groups. Doesn't impress me much because it's ubiquitous, but SU3 is
there's a very
reason. Unusual. So this is the group that represents the strong force that holds our
Well, you see, there's a thing that SU3 gives you this you can gauge it. So you have there is a difference between the SU2 and the SU3 that the quantum chromodynamics, if you like, which is the theory which comes from gauging SU3, is a genuine gauge theory. But when you try and do it for SU2, for the electrons and neutrinos,
weak isospin,
the gauging it doesn't really work because you've got a special. It's not the full group and so on. So there's something funny about it.
Okay.
And there are other theories which might be a more promising way to go. Let's not go into that because this is all guessing. But the idea is that you could develop a particle physics using many twistors.
We're going to have it, in other words, if I'm not misunderstanding you, the idea is that the extra data, we have a problem in the standard model in that we have effectively an origin story with two gods. There's the God of Einstein that gives us space and time, and then there's this other God that gives us SU3 cross SU2 cross U1, which give us the non-gravitational forces and all of these particle properties we call quantum numbers. Sure. And this has no connection to the space and time data.
Well, that's the sort of thing, yeah. It looks as though it's quite separate. They must be tied up at some stage, but we haven't got to that. But the idea here was to try and do it via twistors. Well, I'm just trying to say that we got very excited about this for a while. And then it was a long time ago because when people discovered charm, I think it was charm, and then suddenly this didn't fit. And so we gave up the model.
And so by charm, you mean the addition of entirely separate versions of the familiar family of matter. So we now think we have three copies of matter where the second two are repeated at higher mass scale.
That sort of thing, yes. Yeah, that's right. And so people it didn't seem so simple at that point. So, the various things didn't seem to fit so well. But I think we should go back to that. From the insights that going from general relativity, there's a long story which should be probably hard to describe here. But the construction, twistor theory starts off as a theory about flat space-time.
That's what bothers me about it.
Exactly. And it's what bothered a lot of people when you see...
I'm in good company then.
I was, at the time, at the University of Texas for a year, and this Alfred Schultz had put a lot of people together who were general relativity experts, hoping that something would come out of it, I guess. And I had an office next to Engelbert Schucking, whom I learned a lot from. And on the other side, I had an office that was Roy Kerr's office, and Ray Sachs was a little way down. And I have to backtrack because the question is, where did twistor theory come from? Now, I had lots and lots of ideas that I was trying to fit together. Part of these were trying to combine the Riemann sphere of relativity with the Riemann sphere of quantum mechanics, and various other mathematical ideas which come into quantum field theory. And they were sort of floating around, and I remember drawing a big piece of paper with all these ideas, which were, roughly speaking, of the nature that the world we see is described by real numbers, but sort of hiding behind it is a world of complex numbers. And they somehow control this world of real numbers, so that the dynamics is somehow controlled by the way the complex numbers work. And this was a sort of vague thought I had. And I couldn't think of a picture in which you added, you see, space-time has 4 dimensions. And I needed to add basically one more dimension because I wanted to incorporate an idea. Again, it's a bit difficult to describe these things on a sort of popular program, but it was an idea fundamental to quantum field theory, which has to do with splitting your field amplitudes into positive and negative frequencies. And Engelbert had impressed upon me that this was very fundamental to quantum field theory. Most people weren't stressing it at that time. And the way to think about this is to think of the Riemann sphere again, and you have the equator of the Riemann sphere describing the real numbers together with infinity, and you've got this complex numbers on one side of one hemisphere and also on the other hemisphere. And the ones which are positive frequency, which is the fundamental thing for quantum field theory, extend into 1/2. So this, to me, was a very beautiful way of thinking about it, rather than splitting everything into Fourier components and taking half of them. And that seemed to me.
But you have 4 degrees of freedom with one extra real degree of freedom.
I just wanted one extra dimension, like the Riemann sphere going from the curve to the whole sphere.
Yeah.
And I wanted it to divide it in 2 halves.
Yeah.
And that was the picture I wanted. And you try to do the space-time, it doesn't work. Space-time is 4-dimensional, and if you complexify, it's 8-dimensional. That doesn't divide in 2, that's just something else. So I knew that wasn't right. Okay. Now, I was in Austin, Texas. I had friends in Dallas. Now, this was the year in which Kennedy was assassinated. And my friends in Dallas were at a dinner, and it was the next place that Kennedy was to go to, and he was going to give a speech. And they all got worried because he didn't turn up, and they were genuinely quite right to be worried because he'd been shot. And this was a great shock to us all. And so we decided we wanted to calm ourselves down, and we went a trip from Austin, where I was, and Dallas, where the others were. And we went off in a few cars to San Antonio and maybe to the coast. And this was to try and recover from the shock. And coming back, all the women folk wanted to gossip and so on. And I was with Pista Ostvart, who was a nice fellow. I like him a lot, Hungarian. But he didn't speak much. So all the others wanted to gossip, and I was sort of left over. And we the two of us went in the car, driving back to Austin. And so I had a nice silent drive coming back. And I started to think about these constructions that Ivor Robinson, he was in Dallas at the time, an English fellow who lived in Dallas, and he constructed these solutions of the Maxwell equations, which had this curious twist to them. And I understood these things, and I realized that they were described by, as you talked about, the Hopf map or the Clifford parallels. These are, you can think of a sphere in 4 dimensions, 3-dimensional sphere in 4 dimensions, and you have these circles which fill the whole space, no 2 intersect, and every 2 link. Beautiful configuration. And I realized that this was the thing that geometrically described these solutions that Ivor had found. And I tried to think about this, and I thought, well, okay, these sort of describe... well, the way Ivor had thought about it is to think of a light ray.
Yeah.
And then you think of all the light rays which meet that light ray. So you've got one light ray and all the other light rays which meet it. And that family of light rays you can have solutions of Maxwell's which point along those rays. So what he did, this was his trick, you move that light ray into the complex. So you add a complex number to the...
So 2 extra dimensions.
Well, it pushes the light ray into the complex. And then you can construct this twisting. You don't see the light ray anymore. It's pushed into the complex. But you've still got the complex family of light rays which meet it in a certain sense. So I try to understand what that looks like. And I thought, you're pushing something into the complex, and you describe it by means of this complicated twisting family of light rays. So in the drive back, I thought, well, let's count the number of dimensions there are, these, as I call them later, Robinson congruences. And I was gratified or startled, or whatever the right word is, to find that the number of dimensions of this family of light rays was 6. 6-dimensional family. What's the dimension of the family of light rays? 5. So the ones you actually see directly are the light rays. That's the real thing, and the thing which governing in the mysterious, complex world. Add 1 dimension. They can twist right-handed, that's one way. Left-handed, that's the other way. Divides the thing into exactly what I was looking for.
Fantastic.
So
and that additionally had this structure of 3 complex dimensions?
Yes. Well, I had to go back and get hold of my blackboard and try to work it out.
It must have been incredibly exhilarating.
So it was a complex projective 3 space. Wow. You have these 2 twisters, and I felt pretty chuffed with myself to realize what this was. You have a 5-dimensional space which divides this 6 real dimensional space, which is really a 3 complex dimensional space, into 2 halves.
So if I'm understanding, you would start off with a 7-dimensional sphere. You take an action by a circle to see the complex projective 3 space, and then you could further quotient that out by 2 spheres to get the 4-dimensional sphere.
Well, you have to have you can think of it as a sphere in.
Maybe I'm not seeing it correctly.
You can think of it as a sphere in.
But you had a complex projective. 3 space.
You can think of a 7 sphere.
Now,